Hello everybody and welcome to the very very last video lecture of the Operations Research course. And in this final lecture we explain the so-called simplex algorithm by doing a small example, and this simplex algorithm is what actually TLPK does when it solves LPs. So maybe a little bit of repetition here. So what have we learned so far in this chapter 12, a look under the hood? We have learned that the optimal value of LP is in the corner of the feasible region. So one way of finding the solution would be to check all the corners. And how to do this? Well, you use the Slack form and then look at the example 12.4, where we set some of the variables, basic variables, set rest of the zeros, solve for the basic variables and check the value in the corner. So this is the two decision variables. We can draw a picture. So this is the picture that shows you how the basic variables and the corners here are related. So looks like that's it. Just check all the corners. But then we had this combinatorial curse, which basically the bottom line here was that if I have 50 decision variables and 50 constraints, which is still a reasonable LP, then checking all the corners with the supercomputers that checks 100 million corners per second, it would take more time than the universe is not nearly as old as this number. So that's infeasible. Checking all the corners would take simply too long. So what do we do then? So I explained this by an example. I'm not going to the theory here. So let's start with the standard form LP as we have started. As we always start with almost always start with a standard form LP. If it's not a standard form, then please transform it. We can always transform LP into a standard form. Then we noticed, even in checking the corners, that the inequalities are kind of nasty. So we want to have equalities, and we always get equalities by adding slacks there. So slack 1 here tells what is the difference between this side and this side. Slack 2 tells what is the difference between this side and this side. Slack 3, difference of this side and this side. And slack 4, difference of this side and this side. So with these slacks that are non-negative, these inequalities, this upper bound becomes equalities. So this LP here can be written in the slack form this way. Then we make a still slight adjustment to this slack form. So it turns out to be nice to have this, consider this z as a decision variable in this system. So we can write that maximize z equals whatever is that first we have maximization of z without any constraints, so without anything, is just z that we want to maximize. And since z equals this, it means that z minus this equals 0. So this objective function becomes formally a constraint. So if you think about it a little bit, you will notice that this original system is the same as this system, is the same as this system. And now in this system, all the data, all the problem data is in this block here with equalities. So we just write, as we do in linear algebra, we forget the variables and just collect the data in a table. So consider this table and then consider this table. So this table here, which is what we call the first simplex tableau, is just this table here written in a more compact form. Each columns here correspond to variables. The first column is the objective function z, second column is the first decision x1, third column second decision x2, then x3, we have three decision variables, and then I have slacks there. Right hand side here is what we have here. The sign constraints are omitted in this table, but they are implicitly assumed to be always present. Row numbers here are just, I want to refer to them as something, so these are not as such part of the table, they are just numbers of the rows. And then now comes the trick. So there is an additional column here called BV. So this means a basic variables. And since I started this table like this, if I set all these x's to equal to 0, meaning that I set them to be NBVs, non-basic variables, that means that then there is just S1 equal appears only in this row, S2 only in this row, S3 only in this row, and S4 only in this rows. These are zeros. I immediately read that Z equals 0, S1 equals 48, S2 equals 20, S3 equals 8, and S4 equals 5. So I have found one corner of this problem. I found one solution immediately. So this table can be read so that I have the problem like this. I set basic variables to be Z, S1, S2, S3, and S4, and I read the solution here. Okay, so one corner is found, and what do I do next? So in a small nutshell, how the simplex algorithm now follows. So first in simplex algorithm, we find our first simplex tableau and basic variables associated with it. All the basic variables are part of the simplex tableau. It's here. Next, let's see. So if I identify this simplex tableau to be optimal, I have a solution and that's it. I can go home. If it's not optimal, what then? Then I try to find a better basic feasible solution or better basic variables and change the table accordingly. So I will change these here and then I will change these too. If that is optimal, good, I can go home. If not, I change again and I change again and I change again. Alright, so this is repeated until the optimal solution is found, if ever. Okay, it's in principle it's possible that this will take infinite time, and so that we'll never find the optimal solution. It's very bad luck if this happens, but it's possible. It has never happened to me except once when I really tried to make it happen, and then I managed to do it. Okay, so now we have our first simplex tableau. So we have to check its optimality. So we have to have some way of looking whether this simplex tableau is optimal. And again, I'm not going to prove this, but it kind of makes sense that the simplex tableau is optimal if this, for example, this is not optimal because, for example, x2, x3 is 0 because it's non-basic variable. And I have negative coefficient here. It kind of means that if I make x3 non-zero, then I have to compensate for this negative value here. So then this right hand side here, so the optimal value z is written here, this will increase. So whenever I have negative numbers here for non-basic variables, it makes sense to make them basic variables, because in order then to compensate this equality, I have to increase the right hand side here. Let's say this same thing yet in other words. So the simplex tableau is optimal if there are no negative coefficients in the first row corresponding to non-basic variables. Okay. So we see that this is not optimal. So it means that we have to change a corner. So we have to change the basic variables. So now there are two things. So one, NBV, non-basic variables, becomes a basic variable. We have to choose that. That's the so-called entering variable. And then there is a one basic variable that becomes a non-basic, so that becomes 0, so we have a leaving variable. So one variable will leave and one variable will exit. Enter. So we make a change. And now we want to make this change as efficient as possible, so that we can soon find the optimal BVs, optimal BFS. Same thing. And how do we do this? And this is the most important part here, so-called improvement routine. So we need to improve the simplex tableau, and as I said, and as I've written here, that's the critical part of the algorithm. So the idea of the improvement is that we want to, this is a bit kind of greedy algorithm in the entering. So we want to enter the variable that gives us most bang for the buck, so to say. And as I intuitively explained, that these small negative numbers here give the best. So this gives kind of 20 increase per unit here. This gives 30 increase per unit here. And this gives 60. So intuitively it's clear that x1 should enter, because that has the smallest coefficient here. Or you can look at the original table here. So here the x1 has 60 associated with. So each unit you get 60 in the maximum. Here you get 30, here you get 20. So obviously it makes sense to have this x1 as a basic variable. Again here, x1 now because of this, because this is written this way. So if I increase x1, that becomes minus 60, that's 0, so this must increase in order to be in balance. And yet I say in another way. So entering variable is the one with the smallest coefficient in the first row. Okay, so entering is the x1 because it has the smallest coefficient, minus 60. So what is the leaving? So one of these, so z is always there, z never leaves. So one of these basic variables, s1, s2, s3 or s4, has to leave. And intuitively, what's the idea here is, now I start increasing x1. Since I increase x1, all these equalities must hold also. So x1 was 0 here before, now it's no longer 0, so this will increase here. So there in this row s1, that is 48, it has to decrease in order for this to be in balance. So in order for this equality to hold true. And at some point I cannot increase x1 anymore, because the s1 would become negative. So I start increasing this, and each row I look how these numbers would decrease, and at some point one of these hits 0. So the slack is eaten. There is no more slack there. And then this variable says, hey, you cannot grow x1 anymore. And then this slack becomes 0, and that slack that first becomes 0 first says that you cannot grow x1 anymore, becomes 0 and becomes our non-basic variable, and x1 becomes a basic variable. That's the intuition how it happens. How it happens in practice? In practice we do a ratio test. So this means that the leaving basic variable will be the one associated with the row that wins the ratio test. The smallest positive value is the winner. And what is the ratio test for each row? It's the right hand side of the row divided by the coefficient of the entering variable in that same row. Okay. Then this here, the idea of the ratio test, I just explained this. So I will not say that again. Instead, let's look at the ratio test. So we are basically looking at this table here. This table is almost the same, so we can look at this. So now here is this x1. We are increasing it. So what is the row 2 limit for x1? It's 48, so that's the right hand side of the row. That's the value of the slack divided by 8. Because each 1 unit increase in x increases here 8 units, and we have 48 units in total there. So 48 over 8, that is 6, is the ratio test for the row 2. Row 3, the ratio test is 20. That's the right hand side, that's the number of increase. That's the number of slack there is, really. And each unit of x1 increases 4 units. So 20 divided by 4, which is 5, is the limit that this row gives. Row number 4, there is 8 units of slack. So that was the S3 in the previous table. And there is 2 here, so it's 4. Finally, row number 5, what's the limit here? We have 5 units, but x1 is not here at all. So we can increase x1 as much as we like. This row will never give us a constraint. So 5 over 0 is plus infinity means that there is no limit coming from this row. So the smallest positive number here is 4. It means that row 4 will be the one that changes basic variable. So row 4, we had S3. So the S3 will now leave, and the entering was the x1. So this table becomes this table. So this table is exactly the same as the previous table, except that now S3 was replaced by x1. And now the key thing here that this is unsolved simplex tableau. So this is the same table, of course, as always, or equivalent. These tables are equivalent all the time. That's the whole point of the algorithm. So now we have different basic variables. And now we have to solve this table in terms of the basic variables. So the idea is that these variables S1, S2, X1 and S4 are variables, are unknowns, and the rest of them, so in this case X2, X3 and S2 will be zeros, and then we solve the system in terms of these. So what does it mean that we solve them in terms of these? It means that S1 should appear only in the row 2. Well, it's already like that. S2 should only appear in row 3. So here 1, otherwise zeros, that's okay. S4, the same thing, that's okay also. It only appears in the row 5, because here is 1 and otherwise 0. But X1, that's not solved. So X1 here, it appears in all the rows except row 5. So we have to have here 0, here 0, here 0, here 1, and here 0 in this table. And how do you do it? And this is the part that I have omitted on the notes, and this is tedious calculation sorry about that. But this is pivoting. So what you do, you pivot with this number so that this appears only here and not in anywhere else. So what is the pivoting? It's the elementary row operations that I do here. So first, this row I divide it by 2, so I will get here 0, 1, 0.75, 0.25, 0, 0, 0.5, 0 equals 4. Then I have 1 here. So this is what happened here. And then I eliminate it from all other rows. For example, I eliminate it from the first row. So I subtract this row 30 times. Sorry, I add this row 30 times to the first row. So then this disappears here. And their other coefficients turn out to be what they are. And Z will be 240 because I add 30 times 8 here. Alright. So pivoting is the hard stuff you have to do here. If you don't remember honestly what is pivoting, check your linear algebra course. So linear algebra is a prerequisite to this course, and we haven't used it so much before. This is where we use linear algebra. Okay. And once you are done, this is rather tedious, you get the following simplex tableau. So now this simplex tableau is solved with these basic variables. So you see S1, which is here, it has 1 on the row 2, 0 otherwise. S2, 1 here, 0 otherwise. X1, 1 here, 0 otherwise. S4, 1 here, 0 otherwise. So back to the optimality checking. Were we lucky? Is this optimal? And let's see, we notice that there is a negative x3 is non-basic variable. It doesn't appear here. It has negative coefficient. So this is not optimal. Increasing x3 will increase z. Okay. So we have an entering variable x3. x2 is fine, it has positive coefficient. x3 is not fine, negative coefficient. So x3 will enter, so one of these will leave. So which one? And to find that out, we perform the ratio test. So row 2, so we are looking x3s that are these numbers, and then the right hand side these numbers. So for row 2 we get 16 divided by -1, it's -16. So that's a negative number, meaning no limit at all. So if we increase x3, this will decrease, so this is not going to go to 0 at all. So the slack will only increase. So this means that row 2 gives us no limit. Row 3 is 4 divided by 0.5, so 4 is the right hand side, and x3 coefficient 0.5. 4 divided by 0.5 is 8. Then row 4, this here, it has 4 divided by 0.25 here, 16. And finally row 5, so it has 5 here, but the x3 that was entering doesn't appear, it has coefficient 0, that's plus infinity, no limit. So is the row number 3, this row, that wins the ratio test? So S1 will leave. So we have the unsolved simplex tableau. So this simplex tableau becomes this. The only change is that this S2 leaves and X3 is there. So we have an unsolved simplex tableau like this. And then, yes, comes the tedious part, pivoting. We have to solve it for these basic variables. So all the previous ones are already solved. It's always the case. So S1 is like this, nothing to be done here. 1 zeros, okay. X3, that's the new one. It appears in many places, so we have to do something with that. X1, it's like this one here, zeros here, that's okay. S4, 1 here, zeros here, that's okay. So we have to solve for X3. And again, X3 has half coefficient here, so we have to multiply this line by 2. So this becomes minus 2, 1, 2, minus 4, 8. So that's this line here. Minus 2, 1, 2, minus 4. Here becomes minus 4. And 4 becomes 8. So we multiplied this row by 2 because 2 times 0.5 is 1. And then we have to remove this minus 1, this minus 5, and this 0.25 by pivoting around this. And this is what happened. So let me just explain for the first row what happened there. So in the first row, the X3 was minus 5, and this is 0.5. So we actually have to add this line, 10 times the first line. So 10 times 4 is 40, so we add it, so this 240 becomes 280. And all the rest of the numbers you probably should understand how they become also. So pivoting, 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 pivoting. That's what you are doing. Alright, now we have the following simplex tableau. So this is solved with these basic variables. So now all the other variables were okay. X3, let's look at that. So it appears in its own row and doesn't appear in any other rows. And let's see now, is this optimal? So what are the non-basic variables? X1 it's basic. X2 doesn't appear here, so it's non-basic. It has positive coefficient, that's fine. X3 is basic. S1 is basic. S2 is non-basic, but it has a positive coefficient, so that's fine. S3 is non-basic, but it has positive coefficient, so that's fine. And S3 is basic. So there are no non-negative variables at all, certainly no non-negative variables. Sorry, negative variables. There are no negative variables here at all, so this is certainly optimal simplex tableau. So we found the optimal. And now what is left to do is to read the solution. And the solution is read, well, it's kind of little bit tricky how you read it. So you read it here that z equals 280, so that's here clearly, that's the optimal solution. And then you read that these variables, S1 is 24, X3 is 8, X1 is 2, and S4 is 5. So at least I can read here that X1 is 2 and X3 is 8. What about the X2? Well, the X2 is not here, it's not BV, it's not basic variable, meaning that it's a non-basic variable, meaning that it's 0. So I actually read that X1 is 2 here, X2 is 0 because it doesn't appear here, and X3, I read it here as 8. That's it. Okay, there is a bonus. Now you might be, if you remember that we considered sensitivity analysis also, and there were these shadow prices and reduced costs. And the simplex algorithm gives those for free. That's why they are so much used in this business, because you get them for free from simplex algorithm. So if you solve an LP with simplex, you automatically solve the dual LP, and you have also the reduced costs and shadow prices. And how do you read them? You read them in the first row here. And how do you read them? The reduced costs are these coefficients of the, so the reduced costs, they were related to the decision variables. So they are the coefficients here for the decision variables 0, 5, 0, and the slacks, they were related, the shadow prices or the marginal prices, they were related to slacks, so they are the coefficients of the slacks in the first row here. So in a way, the duality here is that the primal problem solutions are given here and the dual problem solutions are given here, kind of vaguely speaking. So that was a small quick glance look under the hood. So I hope that you now have some idea how the simplex algorithm works, and from the previous section, the truth is in the corners. From that, I hope that you understand why we have to use some kind of more clever algorithm than just looking at the corners. So that was the simplex algorithm. Then we have a couple of final exercises. So exercise 12.9, exercise manual labor. So yes, now you have seen how to use the simplex algorithm, so do it once yourself. So there is a following LP given in a standard form actually, so solve this by using simplex algorithm. It's hard work, I promise you. And then let us end these notes in a kind of, well, unfortunate thing here. Something for you to motivate you for further study. So exercise 12.10, simplex fail. So I have cheated you a little bit. So the simplex algorithm that I presented here, I said that I started with a standard LP like this and then show you how you find a solution. But what was important actually, I didn't emphasize it. I really kind of cheated here. Sorry about that. Is that all the components of the b's are non-negative. So this upper bound b's are not allowed to be negative numbers. If it has a negative components, this algorithm that I explained, it will fail. It will not work. And the question is why? Why is this? And then that's the first part. This is maybe not too difficult, but you have to carefully understand what's going on there. And then an extremely difficult question. Can you figure out a solution? What to do if there is a negative number there? And for the first part, yes, it's not too complicated to find out where the mistake is, but you have to understand the algorithm relatively well. And then a solution, there are many solutions to this. I just mentioned for you to Google. There is a big M trick that's possible to use here. And then there is a so-called two-phase simplex algorithm. So somehow this algorithm that I presented here is split into two phases. So the first phase is something that you do if there is a negative number, and then the second phase is pretty much what what is the normal simplex algorithm. Alright, that was all there was in this course. I hope you enjoyed. I hope you learned something too. This is the end. Bye.